In this question, what we have is we have a magnet. It's being dropped into this solenoid, and we have to figure out, well, what direction is this magnet traveling to cause this induced current that we see here? And we also have to figure out, well, what is the direction of the North Pole and the South Pole based on the electron flow? So the first thing that we need to do is we need to figure out, well, what hand are we going to be using? In this case, we're talking about electron flow, negative charges, so we're going to use our left hand. And if we put our left hand and place our fingers in the direction of the electron flow, we see that they're moving to the right here. Our thumb then points in the direction of the north pole of the magnetic field. So that makes C the north pole, and therefore default is B is the south pole. The next thing we have to figure out, well, is what direction is this magnet traveling so that it's causing this induced current in the wire. So is it being dropped or is it being pulled away? And Lenz's law states that the direction of the electron flow is such that it creates a magnetic field that opposes the motion of the magnet that originally created it. So the easy way to think of this is, what direction does the magnet need to travel that would be difficult based on that induced current? So in this case, if we take a look at this, we know that this is the North Pole, this is the South Pole. What would be difficult to do? If I move this magnet upwards, South Pole and South Pole are going to repel each other. That's what would happen naturally. So it's going to be such that it opposes the motion. So south, bringing it towards south, those don't want to happen naturally. That would be difficult to do, and that's what direction the magnet must be traveling to create this induced magnetic field, because the magnetic field is going to be such that it opposes the motion of this magnet. For the second question, it's going to be very similar logic. In this case, we're given what the north and south poles of the magnet is based on that electron flow that's been induced by the movement of the magnet. So in this case, again, we're going to use our left-hand rule because we're dealing with negative charges. We place our fingers to the right, and our thumb goes in the direction of the North Pole. In this case, that's what we're given. North is here, so our thumb points down. That means our fingers are going to the right. And if we could put our eye right at eye level and look across the solenoid, what we would see is, based on the movement of the electrons, they would be going clockwise. And the question is then, well, what direction is this magnet traveling to cause this induced current? And remember, the induced current is going to be such that it opposes or creates a magnetic field that's going to oppose the motion or make it difficult to happen. So if I want to move this magnet close towards this solenoid, well, that's what happens naturally again. The north and south are going to be attracted to one each other, so that's not going to create an induced current. Instead, if I move this solenoid out, or this magnet out of the solenoid, away from the solenoid, that's what's going to cause that induced current and the magnetic field that we see. So in this case, the magnet is being pulled away or moved upwards, away or out of the solenoid. So I hope that helps. If you have any questions, just contact me in private discussions.